Hello, my name is Anthony, and I have the pleasure of presenting some work I did on floating point error analysis using step functions. So first, just a little bit, floating point numbers are ubiquitous in computer science. We've all used them before. Anytime you want to work with real numbers, you end up using floating point numbers. From high consequence systems such as avionics to industrial control systems to machine learning. They're undergraded at everything. Despite this widespread use, they're pretty imperfect. And this imperfection causes a deviation from if you were doing an exact calculation. So I've got kind of a silly example here, where if you write in JavaScript 0.1 plus 0.2, it doesn't equal, as you would expect, 0.3. And part of this is because 0.1 is not exactly representable in the double precision format. While this is kind of a trivial example, you can see how this sort of subtle error in a more complex, hello. Okay. You can see how in a more complex system, this sort of deviation from what you would expect can propagate and cause different errors in behavior. So the goal of this work is to help programmers manage this error and understand really what's going on. And so the way we went about this is we developed an abstract domain using step functions that will not only give them a bound on the error, but also give them some insight into the nature of the floating point error in their program. Before I dive into the abstract domain, though, I need to talk a little bit about some of the fundamentals of floating point numbers that we leverage in our abstract domain. So some background here is a floating point number is represented by a mantissa, m, a base, beta, and an exponent, e. The format is actually defined by the base, which remains constant for all the floating point numbers in the format, and a maximum value on the exponent. And so the only things stored in memory are the mantissa and the exponent bit patterns. And to get the actual value out, you have to run this equation. This format has some interesting consequences for the behavior of floating point numbers. Here we've got a diagram of the real number line, and each of these vertical bars represents a representable floating point number. Here's an example calculation where we have two representable floating point numbers, a and b, and we multiply them together, and we end up with a non-representable result. When this occurs, you have to round the floating point number. You have to round to a representable floating point number. And this difference between what you would have gotten exactly and what you're forced to store in the computer is the source of this error, and this is called the round-off error. However, this is a little bit of a simplified diagram, because in reality, you get something closer to this, where the difference between representable floating point numbers changes in size depending on where you are in the number line. So you can see around 0, we've got a certain step size, and then as we pass this boundary, we end up with a larger step size between adjacent floating point numbers. These regions are called binades, and they'll become important in our analysis. The cause of this is the exponent. So when you're incrementing a number, a floating point number, you're incrementing the mantissa or decrementing, and the actual change in value is going to depend on what the exponent is. As the exponent increases, your change in your step size is going to increase, and if the exponent goes lower, then your step size is going to go lower. And one of the key things here is as you get closer to 0, you're going to have more and more fidelity towards what real numbers you can represent. This also has another knock-on effect, which is there's a lot more binades near 0. Which will become a little bit more important later on. I've been saying the word step size, but what I've been referring to as step size is typically called ULP, or the unit in last place, which is just the distance between the two nearest representable numbers. Because this step size changes depending on the magnitude of your variable, you can think of this as a function from some real number to this distance between the two nearest numbers, representable numbers. So if you have a real number lying in here, the ULP is just this distance here, which remains constant over the length of a binade. So in our analysis, we'll be using this ULP to actually bound the round-off error of any operation. So before we had some multiplication operation, and if we don't want to calculate exactly the round-off error, we can provide a sound upper bound by just saying it's going to be below the ULP of whatever that number would be. In particular, there are multiple rounding modes, but the one that's most common by far is round to nearest, which means round to the nearest number. So we can actually bound the round-off error by 1/2 of the ULP. While we focus on round and nearest in our paper and in this presentation, it's pretty straightforward to modify the analysis for another rounding mode if you want to use that for whatever crazy application you have. So I've gone over all this background. Does this actually matter in real life? We ran an experiment on a sign approximation to see how the error actually behaves. On the x-axis, we have the output of the sign approximation and on the y-axis, we have the absolute error, which is calculated as the difference between the approximation using a double precision format and a 200-bit precision format. We have a histogram here showing all the different data points, and you can see pretty clearly as we get closer to 0, where the step size or the ULP decreases, the round-off error actually gets much lower. And even nicer, we can see these very clear lines here, which are right on the binade boundaries. So as we cross that binade boundary, our round-off error gets much lower. So this is sort of the nature of the floating point numbers, which can be very complex as you get higher, as you have longer and more intricate programs. But clearly this has effect on the actual error that you see. And so our goal is to use this behavior to provide a nice error bound for the user. When doing static analysis, we know a possible range of values for a variable. And typically people will give a single error bound for that variable. However, this range of values can actually cross over a binade boundary. And we can utilize this fact to provide multiple error bounds for that variable depending on the binade boundary, which will allow us to tighten the error bound for these binades closer to 0. And so this is sort of the key idea of our paper, is that we can leverage these binade boundaries to not only get a more precise error bound, but we can also present to the user a better understanding of how the error will manifest in their program. I'll talk a little bit about our abstraction scheme now. So our abstract values are called segments, and we represent them as a tuple containing an interval, which is the range of values, interval containing the range of values that are possible for the variable, as well as a positive real number for the error bound. We write segments in a pretty standard way, but because we want to actually split and provide multiple error bounds across binade boundaries, we actually consider sets of these segments. And a set of a segment, if you really think about it, is just a step function, a piecewise constant step function. And so here's just a little diagram with two segments, one going from x to y with a certain error bound, and another going from y to z with a slightly higher error bound. So we'll abstract our floating point variables into a single segment step function. We form the interval by rounding the floating point number up and down, and we bound the error on that floating point number by just taking 1/2 of the ULP of it. The reason we have to provide an interval and an error bound here is because programmers don't always write exactly representable numbers in their programs. A good example is the 0.1 I was talking about earlier is a fairly reasonable number to write down in your program, but actually isn't exactly representable, and you're automatically incurring error when you write that. Once we do this, we'll have some segments, and we need to propagate the error through, and we do this by defining segment arithmetic. Segment arithmetic is just performing typical arithmetic operations over segments. So we have to find the new interval. We just do this using standard interval arithmetic, pretty well studied. And then we propagate the error using specific error functions for each operation. The error function has to take into account sources of error from two different places. The first is the existing error of the operands, colored here in red. And the second is rounding the result after it's been calculated, colored here in blue. So we can calculate the existing error, how the existing error propagates by taking the worst case values of the two intervals and seeing how that might propagate into the result. And then similarly for the rounding error, we take the potential result with the highest magnitude and we give that we throw that into the ULP function to understand the largest possible rounding error for our segment. We've defined some operators here for notational convenience, but they basically just take the result with the highest or lowest magnitude in your interval. This is really great, but the problem is we haven't actually split on the binades yet. So in order to handle this binade splitting, we have to modify our segment arithmetic slightly. The first thing that we do is we calculate the interval the result of the interval arithmetic to get the output interval of our result. And then we want to create a set of segments so that we can provide multiple error bounds. We will then calculate the error bound for each of these split intervals using a modified error function. Here we've modified the error function, and so it takes in addition, the interval that we're actually providing the error bound for, and then we just update our rounding error term to include the worst case scenario, so the largest magnitude. Because if you recall, as the magnitude gets larger, the ULP will increase. We have to include the original intervals as well for the error propagation terms here. And so that's why we end up splitting calculating the interval arithmetic first rather than along the way for each binade. There's a problem here, though, is that we've defined our segment arithmetic over individual segments, but the result of the segment arithmetic produces a set of segments. If you recall, a set of segments is really just a step function, and so we have to define arithmetic over step functions. So to do this, we perform segment arithmetic on each of the each combination of the underlying segments in each step function. So here we just perform the arithmetic operation we've defined for segment arithmetic on each underlying segment, and then we need to perform a merge operation. The reason for this merge operation is that there's a possibility that these segments can overlap. So here we have an example where we're subtracting two step functions. The first has two segments, one going from 2 to 4 with some error bound, and the second one going from 4 to 8 with a different error bound. And then we're subtracting from that a single segment step function going from 1 to 3. When we perform this operation, we end up with two segments in our step function, one from -3 to 3, and the other from 1 to 7. And these intervals actually overlap on these segments overlap on the interval from 1 to 3. And so what this means is you actually have overlapping error bounds. So we have to find a way to ensure that these error bounds, we have to find a way to pick the appropriate error bound. We do this through the merge operation. The idea is pretty straightforward. You just want to pick the higher error bound for any overlapping interval. Here's a diagrammatic view of it. We've got two segments here, X colored in orange with a certain error bound, and Y colored in blue with another error bound. When we merge these two, we form the step function Z, which just truncates the segment with the lower error bound on the interval and the overlapping interval. This is now that we've done this, we're no longer chasing our tail, and we can perform arithmetic on segments, and we can propagate it through the program to find the error bound of our variables. We've implemented this abstract domain in a static analyzer. The users will supply some C code as well as input ranges for all the parameters. Here's an example of the C code with the sign approximation I was discussing earlier, as well as the input, how they might define the input ranges. From here we have X going from 0 to pi over 2. The analyzer will output the segments for all of the variables. To do this, we represent it as a CSV, where each row defines a variable called retval here, as well as a segment with a lower bound for the interval, upper bound for the interval, and then an error bound. And this CSV will give you all the information you need for your step function. We've run this analyzer on a selection of FP benchmarks, which is a standard floating point benchmark suite, and we compared it with the Fluctuat static analyzer. So we have a similar graph here to the one I showed earlier, where your output of your function is on the x-axis and the error is on the y-axis. We've added the error bound that Fluctuat gives as a straight orange line, and the error bounds given by our tool as these green lines. For the sign in the top left here, you can see that we improve upon the error bound for values closer to 0, and our analyzer produces an error bound that mimics the nature of the floating point error. As the floating point error experimentally seen goes down, so does the bound we've given for our analyzer. If we move on to the Doppler 1 benchmark, we see a similar pattern where we mimic the behavior of the floating point error And we improve upon the actual bound given by Fluctuat for certain subranges of the output. Rigid body 1, we don't actually improve upon the error bounds, but we do give the user a clearer picture of the behavior of the error in their program. So they can see where the error might be larger and where it might be lower, which is more information. Square root's an interesting case because the error actually proves to be flat. And so in this case, giving a single error bound produces a better result in all cases, but our step function analyzer will show you that the error bound is going to be flat without having to run costly experiments. One thing to note here is the number of segments we've listed here, and this will become important later when we talk about performance. It's particularly for the sine one, we end up with 4,167 segments. For certain programs, the number of segments actually produced for that variable is much lower, which is better for performance. Another benchmark we ran on that was pretty interesting is called CAV10. And this is interesting because it deals with branching. So there's another problem with floating point numbers and error that I haven't quite mentioned yet, which is known as branch instability. And the idea here is that if you are running your calculation using exact precision, then you might take one branch, but because of floating point error, you might go down another branch. And so this produces kind of an odd graph, right? You've got this split in the middle where you can see the two different branches, and you can provide error bounds for both of those. Fluctuat has a flag for you that allows you to say if you want to be sound in the presence of branch instability or not. If you do say that, then it'll give you a much higher error bound because branch instability will usually cause you to have a much higher error because you're executing different logic. If you don't, it'll give you a very nice error bound, but it's not sound in the presence of these errors. A nice part about the step functions is we can actually show how the branch instability changes depending on which branch you take. So on the left here, you can see that in the branch unstable case, we have a higher error, whereas in the other branch unstable case, if we were to go down the wrong path in the different case, then we'll have a lower error. Fluctuat only gives you the error bound for that top error. And so you can see how our tool gives once more insight into the actual nature of your floating point error. Branch instability was a little bit tricky to define the semantics for. I won't go into details of all this. It's kind of detailed. It's kind of intricate. But the basic idea is you have to determine if you have a possibility for branch instability and then compare the error for all stable and unstable paths. Talking about performance, our tool runs about an order of magnitude slower than Fluctuat, and this is because we're providing multiple error bounds rather than just a single error bound. In particular, step function arithmetic proves to be rather costly. Because we're performing operations for each segment in both of the step functions, the runtime grows with the size of both of those step functions. In addition, merging can be rather tricky as well. The tricky part is that you have to determine where these intervals overlap. And so we use a pretty naive implementation in our current code, but this could be improved using a more special purpose data structure. In conclusion, we think that taking into account binades will allow us to improve the error analysis in two ways. One is actually improving the error bound for certain ranges. And two is to give users a clearer picture of the nature of the floating point error in their program. There are some clear areas for future work. The first is that we didn't actually improve error bound in all cases. And the main part of that is that we were using intervals as the underlying value domain. Fluctuat uses zonotopes. And so if we define our value domain over zonotopes, then we could potentially potentially have our worst case error be the same as the error Fluctuat gave, or some other more accurate analyzer. There's some work to be done about how do you do binade splitting over a relational domain. That sounds pretty interesting. Another one is performance. Performance was slower, and the benchmarks that we were using was fairly small code. And so you can see if you have a much larger piece of code, this might take quite a while to run. The performance is directly impacted by the number of segments that were produced by our analyzer. And so one idea we've had is allow the user to control the number of segments. In particular, the amount of binades grows as you get closer to 0, but their size gets smaller. There's the same number of binades between 0 and 1 as there are between 1 and the max float. And so do users actually care about this level of fidelity near 0? Perhaps, perhaps not, but we can give them control over this, which will allow them to improve the performance at the loss of precision. And lastly, I didn't talk about the language features that we support for this abstract domain, but we support a limited subset of C, and we're missing a few key things. Functions is obvious, but loops is the one that I'm particularly interested in. I've taken a few stabs at defining widening and narrowing operators, but none of them have produced really nice results. Thank you. Any questions?
Let's see if this works. So questions? There's one here.
Yeah, thank you very much for the talk. So I may have missed that, but so you mentioned that one cool advantage of your technique is that you can provide more information to the users compared to Fluctuat. Like you have a stepwise functions that give you, even though they are not necessarily close to the error, they give some information on the shape of the error. Is this something that you can guarantee? Like, do you have some theoretical results on the fact that if your step function is higher somewhere, then the concrete error also follows this behavior?
Yeah, that's a good question. We don't have any theoretical results showing that the stepwise is going to necessarily mimic the error. And I actually think it's not necessarily going to mimic it exactly. So if you have, these are rather simple outputs to our error, right? But you can see with rigid body that things can get a little bit more complicated. Or even in the square root, we just have a flat error. So if you have a very complex floating point program, this error could have kind of very strange shapes. But I do believe that even if you have something kind of strangely looking and maybe even a little bit more continuous, then this will mimic the behavior better than this will mimic the behavior at some level.
Thank you.
Okay, another question, next question.
Am I right in thinking that for many analyses, the bounds are essentially like minus min double and positive max double? In other words, you have no idea. Like in your case for the function on sine, you took in a parameter x. But you immediately said that the bound was down to pi over 2 or something like that. I didn't see that. Looking at the code, it looked like it would have just stayed as really, really large bounds. So.
Oh, yeah. Perhaps I misspoke. The users will have to input a bound on the parameter as it goes into the function. And so not that the output bound on the error, but they'll have to know at least on some level what could possibly be passed into their function. Yeah, in order to provide a sound analysis on all different inputs.
Yes?
In which static analyzer did you implement the domain?
We have our own built static analyzer. Yeah. Mm-hmm. So we implemented all in OCaml using SIL for the parser.
Okay.
Potentially to integrate with Promise-C down the line.
Okay.
Yeah.
Okay, good. Thank you.
More questions? So you discussed this interest of trying to bound the number of segments. Did you experiment with what would work well?
We haven't gotten that far yet. I think I ran some very preliminary experiments when I was running into long-running analysis. And in typical, I would just say if anything is below like 0.002, it's all the same segment. And that worked quite well. But there's more experiments will have to be done to understand, what might be a good way to bound it.
Okay. Right. If there are no more questions, then thanks a lot.
Yeah.